Hello, hello, and welcome everyone to the Varsity Tutors StarCourse series, where today's virtual field trip is taking us on an adventure into the brilliant brains of some incredible innovators. From inventors to scientists to astronomers and beyond, we're going to be learning all about what has inspired and allowed some of the greatest minds of our past to accomplish all the wild and wonderful things they've done. Now, there are going to be plenty of opportunities along the way to participate in today's journey, so we may chance to ask some questions, and we'll certainly have the chance to answer some. So feel free to use the chat on the right-hand side of your screen to both ask and answer questions throughout the lesson. If we don't get to those questions right away, not to worry, we're going to save about 10 minutes toward the end of the lesson specifically for Q&A. And with that, I'm going to go ahead and hand things along to Ben with the Omaha Children's Museum to get us started.
Hey everybody, thanks so much. My name is Ben. I'm calling you guys from the Omaha Children's Museum. I'm so glad that you guys decided to tune in. Today we're going to be talking about the great minds. And when I talk about the great minds, just like Haley was saying earlier, we're talking about the great minds of science. So I don't know, maybe some of you guys, if I say the great minds of science, maybe you guys can think of who would the big people in science, who would they be, inventors or thinkers or scientists. So let's see, can you guys think of some people? I mean, some of them you may know that are doing stuff right now, maybe some inventors. So some people like me say like Albert Einstein. You guys know Albert Einstein? He had the big poofy hair, the big bushy mustache, or E equals MC square. Or there was Thomas Edison. Everyone know what Thomas Edison did? The light bulb? Yeah, I mean, that's big stuff. Isaac Newton. Isaac Newton, the three laws of motion, that's big stuff. Well, you know what? Forget those guys. I mean, they're very important. It's a very big deal, but let's just don't forget them, but put them off to the side, okay? Because I'm going to be talking about some other great minds. And these great minds are people that talk about all kinds of different sciences, and these are people that have made discoveries and learned new things, and maybe you've never even heard about them in the first place. So I've got a few that I want to talk about. The first one is an oceanographer, and this oceanographer's name was Sylvia Earle. And Sylvia Earle was very important because Sylvia Earle, you know, she studied the ocean, oceanography, study of the ocean. Makes perfect sense. So Sylvia Earle did all of this exploring of the ocean, but Sylvia Earle didn't so much explore the top part or, you know, the middle where all the stuff is or the animals inside. No, Sylvia Earle was all about the bottom of the ocean. Now, have any of you guys ever swam in the ocean before? No? Or maybe some of you, maybe you've been in the ocean, maybe you can touch your toes at the bottom of the ocean. Have you guys gone far enough and out and you can't touch the bottom like that, where it gets kind of scary? Well, do you think that you could go way out and then swim deeper and deeper and touch the bottom of the ocean floor? Do you guys think you could hold your breath? Do you guys think you could swim deep enough? Do you think that's possible? Well, I'll tell you what, Sylvia Earle did it. Sylvia Earle did something that's very phenomenal. Sylvia Earle did an ocean floor walk. So if this is the ocean up at the top, all the way at the bottom where there's sand and there is other marine life, Sylvia Earle dove down to the bottom and walked around. So when I say she dove down, she didn't swim and her ears didn't pop, she didn't have to take a deep breath. She actually got in a suit, kind of like this one. And then I kind of use this. Maybe we want to get a overhead shot of this. I use this just as kind of a demonstration. Maybe I think I need to hold it up like this for you guys to see. I use this as a demonstration just so you can kind of get an idea. This actually goes in a fish tank, so we're not going to really, it's not exactly what Sylvia Earle wore, but she wore something kind of similar to this. Now, it looks like a scuba suit, and it is in a lot of ways, but this suit is something called a gym suit. And the difference between those two is a scuba suit has a supply of air right here at the back, but a gym suit goes all the way at the top. So Sylvia is all the way at the bottom. Now, tell me, you guys look at the way that this character is dressed. It's this big suit. They've got this big giant helmet on. This big suit seems to protect their body. Does it look like any other suit you see any other scientists wear? Look at that big dome head. They got to get their oxygen. Do you think maybe they look almost like astronauts? I kind of think so. So Sylvia Earle went all the way to the bottom of the ocean floor. The cool thing about Sylvia Earle is she didn't just kind of stay there. She stood there and was able to walk. And Sylvia Earle walked 1,020 feet along the ocean floor. I don't know if you know how far that is. That's about as tall as the Eiffel Tower. And that holds the world records. It's a lot of steps. So that's one of the great minds. Sylvia Earle, along with her gym suit, was able to walk across the ocean floor. Not a lot of many people know about it, and I wonder if you guys could do something like that too. But I've got more scientists, more things to talk to you about. Now, this is a cardiologist. Anybody here know what a cardiologist is or what a cardiologist does? See, here's the thing. With some of the scientists I'm talking about today and some of the different kinds of science, I'll tell you the name of the science or the kind of scientist it is, but you won't always know what science they do or what that means. Well, let's break it down just a quick second. So cardiologist. Well, what does cardiology mean? Well, maybe you've heard it somewhere else. You know, when people are doing calisthenics, they're doing cardio work. Well, I'll tell you what, that word comes from Latin. Cardio means of the blood or of the heart. Now, you're like, well, why are we learning about Latin? Well, we have to go back to our friends, the Greeks. Now, the Greeks are very, very helpful when we come to terms about the law or terms about science or medicine. Basically, what they did is the Greeks and the Romans, they decided to invent their own language. So whenever they spoke about the law or medicine, those really, really big, important things, they could say, all right, we're going to agree cardio means blood and of the heart. Everybody good? Good. Bingo. So whenever you hear some of those older sounding words, chances are they came from the Greeks and the Romans and that Latin origin. So cardio means of the heart. So a cardiologist probably deals with of the heart and of the blood. And that's exactly what the next scientist is, the cardiologist. This woman's name was Helen Taussig. Now, the heart, where is your heart in your body? Is it somewhere around in this area or maybe around your kidneys or up here? No, no, no. Your heart is right back there. Now, your heart is a very important muscle. It's not an organ, it's a muscle. Now, do you guys know what a cardiologist does, so what the heart does? Any ideas? Do you know what your heart does? Can you hear your heart right now? Maybe put your hand on your heart. Do you know what it's doing when it makes that boom, 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 boom? It's helping pump blood throughout your body. Throughout your entire body, blood is cycling through oxygenated blood using that muscle of the heart. So when you have a very important muscle like your heart, you want to make sure you're taking really good care of it. And if you have an underdeveloped heart, or let's say some kiddos are born with a defect that, you know, their heart doesn't quite work as well, well, Helen Taussig developed something called the shunt. Now the shunt, let's say this is my heart. All right, now it's not my heart, it's not a real heart, this is just kind of my demonstration heart. So I didn't make it look too much like a real heart because it would be like dripping and bloody and stinky and gross, and I don't want to put you guys through that. So let's say this is my heart. So it holds some blood in here, and it's got some veins here. Well, what Helen Taussig did with her shunt is she was able to create her own veins. Well, not her own veins, but she was able to take pieces of plastic that would function as a vein. So if that blood could not go through the body in a perfect way from the heart to the rest of the system, she could create her own veins. So let's get a shot from up here at the top so you guys can see. Perfect. So there is my heart. And let's say these are the veins going through that system. Or let's say that this is one of Helen Taussig's shunts that help go through. Well, just like I was saying, it's a muscle. Have you guys ever flexed your muscles before? When you actually, could we split the screen, please? Or put one, perfect, right over there. So if you flex your muscles, you're flexing something. Well, that's exactly what my muscle is doing. It flexes and pumps that blood. So let's get a close-up of my heart again, please. So I'm going to put this right here, and I am just going to squeeze this section right here. It's a little bit of a balloon right here. Let's see what happens when I squeeze my balloon right there. Let's get a nice... Gross. Look at all the blood. Look at the blood going everywhere. Oh. But all I'm doing is I'm squeezing that top. I'm using that muscle to squeeze all of that up. Isn't that awesome and gross? I love it so much. Oh, you can do even more. Don't worry, it's not real blood, it's just Kool-Aid, but it was so tempting not to put like a lot of red dye in there and really gross you guys. Okay, I'm gonna do this forever. I gotta put it away. So that is another example of some of these great minds. We're talking about the heart and helping people live. We're talking about people walking across the bottom of the ocean floor. Now, this is something a little bit different. Now, just because you're a grown-up and you've been around forever doing all of this science stuff does not necessarily mean that you can't be a great mind. In fact, I want to talk about someone really cool. This was a young woman named Jitantan Jalangi. And that's kind of a weird name, but this is a young girl. She lives out in Flint, Michigan. She is 16 years old. I don't know if you have ever heard of something called lead poisoning that happens in the water. Basically, if your house is a little bit older, like maybe anything built before 1980-ish, some of those pipes can corrode or rust or break down. And when all of that corrosion and rust occurs in those pipes, it can get into your drinking water. And those things cannot be very good for you. It can cause, problems with kiddos or problems with your respiratory system, things like that. So anytime we find lead in any sort of water supply, we got to get it out of there. We got to patch up that corrosion, or we got to replace those pipes, or we've got to repair any of that area in that water supply. So this young woman was able to develop her own system of lead detection, and she developed her own app. You guys know what I'm talking about when I say an app? It's that thing on your phone, so you're not playing Candy Crush and you're not, talking to your friends or whatever. No, this was a special app to help navigate and treat lead poisoning in water. I think that's the coolest thing in the world. This young woman has been on TED Talks. She has gotten all this funding in different sources, and actually probably the whole world is going to see an actual prototype for this device in about 2 years. So I don't have that device with me right now, but I want to show you a little bit about how lead works. So I've got just basically, this is a supply from the museum of a little bit of water. So I haven't had any of this water to drink or anything like that, but I thought right here, let's see what the lead is like on this water. So let's take a look. I mean, it just pretty much to me looks like a regular clear glass of water. It doesn't look like there's any funky thing growing in there. It looks okay, but looks can be deceiving. So I'm going to take a little, and actually if we can get that dropper up, I'm going to take my little tiny pipette here, and I am just going to squeeze out a nice supply of water, just like that. So I'm getting all of this water just up in here. Perfectamundo. Now I'm going to take some of my water and I'm going to put it right here in this little tube and fill it up. Perfect. Awesome. So that's all I need. So this is actually going to be my sample of water. Now I have this lead detector strip, and what I do is I'm just going to put it right here in the bottom. I don't know if you guys have had any COVID tests. These kind of look the same way. All I have to do is just give it a little splash around, and I'm going to let this sit for probably about 10 minutes. And we'll check and see on it, make sure my lead levels are safe, or if maybe the pipes and the corrosion here at the museum are something we need to worry about. So fingers crossed, let's check on that a little bit later. I'm going to move some of these things out of the way. By the way, I don't know if you guys are ever nervous about lead, or maybe some moms and dads are out there and they wonder about that. This is actually from a kit that you can just purchase at home for your own use, just to make sure that your own lead supply is safe at home. But you know what? That's something for another day. So let's talk, let me get this out of the way. Let's talk about another kind of science, okay? This kind of science, maybe you guys have ever heard of this kind of science. This is called chemistry. Anybody know what chemistry is? Yeah, what is chemistry about? What is a chemist study? Okay, so I tell you what, I'm kind of tricking here because chemistry is about a lot of things. So remember, we're going back to the Greeks here on this. So chemistry, chem, goes back to the makeup of everything. Wow, that's a lot of stuff. And it is. Chemistry is a lot. But it's talking about everything and what puts things together. So if you have a little bit of water that I had earlier, so what are the little tiny things that make that water up? Well, you've got H2O. That's what chemistry is really based in. So I want to go to my chemistry right over here and talk about a scientist named Joseph Priestley. Joseph Priestley was a cool dude because, well, I'll explain it to you. Everybody, take a deep breath in with me. 1, 2, 3. Hold it. Hold that deep breath in. Everybody got it. Keep it in. And relax. Okay, good. Good job holding that breath in. So, question for you guys. What was the thing that you just breathed in? You guys took a deep breath, you brought it into your system, you held it into your lungs. What was the thing that we all breathed in? Do you guys know? I think some people are saying oxygen, and you are absolutely right. And when you exhaled, when you let all of that stuff out of your lungs, what was the stuff that you exhaled? Does anyone know? I'll give you a hint. It's not oxygen. Anybody? I'll bet someone out there, carbon dioxide. You guys are brilliant. Well, here's the thing about Joseph. Joseph, at the time, a lot of people thought everywhere around us, all that gas, all that thing, that stuff we can't see, it's all oxygen. Every little bit. So every little bit, it's always oxygen. Well, it's not. That's what Joseph thought. He's like, I don't think that's so much right. Well, if you have a theory, and I bet there are a lot of scientists that know exactly what I'm talking about, if you have a theory, if you have a guess, if you have an idea, well, the only way you can really know what's right for sure is to prove it. So let's prove it. Let's prove that this whole area around us, all of the gases around us, are not just oxygen. Well, let's think of oxygen. Oxygen is flammable, for example. Like if I were to light a match, oxygen would burn, just like paper. Paper is flammable. A big giant piece of metal, I would put something like that, it would take a long time to melt. It wouldn't catch fire. But oxygen is flammable. So let's showcase this a little bit. I've got a little tiny candle here, and I have a lighter. Give me one quick second. I'm going to turn off the lights so you guys can, strangely enough, even though we will be in the dark, you'll be able to have a better view of what I'm doing here. So I've got my little tea light. If I could get my overhead view, please. Thank you so much. So I've got my little tea light, and I'm actually going to light my candle right here. Oh, it's so beautiful. I love it so much. So right now, it's sitting there and it's burning all of this oxygen that's around me. So I'm going to take a little tiny jar that I've got. Oh, look at that. It's so pretty. So what I'm going to do is I'm going to take the open end of the jar and I'm going to put it upside down and I'm going to lay it on top of my candle. Now remember, that candle is burning oxygen. Now I wonder what will happen if I put my glass over the candle. So let's see, if this is all filled up with oxygen, it'll just burn and burn and burn and burn, right? Or maybe not. Well, let's find out. So I'm going to put my glass right on top, and it looks even more beautiful than it did before. So remember, oxygen's flammable. That's the whole reason why the light was able to stay lit the whole time. But now I've got my glass covering it, and it's still burning that oxygen inside. But now you can see it's getting darker and darker darker and darker, and finally, the whole thing goes out. Now, that tea light is all done. So, let's try it again. I'm going to light it again just to show you that I'm not making this stuff up. Come on, you stinker. There we go. I'm going to light that again. So what's happening is all of that oxygen around us, in fact, all of the oxygen that's inside my jar, it is burning all the oxygen inside. Now, you still see stuff inside, but that's because there are other gases around us. There's the carbon dioxide, like you just breathed out. There's even a little bit of nitrogen in there. So even though you see an empty portion of the glass, that's what's in that glass, those other gases. I'll show you again. If I cover this up, only so much oxygen is in there for that to burn. So it's going to go, and I'll even show you. Just before it goes out, I'm going to take the top off, and when I take the top off, it'll be exposed to the oxygen that's around me just like that. Pretty cool, huh? So once I cut off that supply, it burns and burns and burns that supply, but all I have to do, since there's so much oxygen around me, I can just whoop, take it off. And it brightens up again. Pretty cool, huh? Let me switch it back on. Perfect. So you notice that these are a bunch of different kinds of science, and I don't think, did everyone even know that it was not just oxygen around us? I mean, it's kind of a cool thought. I never would have thought to make a guess as to, hey, what's all this other stuff around me? I just think that's I think it's a great mind to figure that sort of stuff. Now, remember how I was talking earlier about Sylvia Earle, the woman that she dove down? There's something really important that I want to remind you about. So the deeper and deeper you dive, I was talking about Sylvia Earle and how she had her special gym suit. Well, the important part of this suit is it protects her. Do you think that if you swim all the way down to the bottom of the ocean, it would be okay for your body? I don't know. Sometimes when you're swimming deep down, do your ears ever pop and it starts to feel pressure? Well, it's because of something called water pressure. Now, water pressure is basically the weight of water. So the deeper you go, all of that water is pushing down on that body. So poor Sylvia Earle, the deeper she's going, more and more water is above her and on the sides of her, and it's pushing down on her body. Well, that's the whole reason why she had to wear the suit, is she wouldn't get crushed. But that pressure can be very strong. Now, is there such a thing as air pressure? Well, we just learned about how there are all of these other gases around us. Actually, did you know that all of the gases around you actually weigh something? I mean, put your hands out there right now. Everyone do this. Do you feel anything in your hands? Does it feel like you're carrying something? Well, oxygen, all those gases, carbon dioxide, everything actually has mass, and it actually weighs something. Now, you probably don't feel it right now because it's been pushing against your body ever since you were a little tiny baby, but it's pushing you on all sides every single time. Think of it this way. This is how air pressure works. Have you guys ever played with Play-Doh? Take a chunk of Play-Doh, you put it in your hand, and you roll it evenly on all sides, on all sides, on all sides. What shape does it make? Do you guys know? What shape does that ball, if I circle around and around and around it? A circle or a sphere. Maybe some of you said sphere, like a ball. That's the shape it makes. Well, when all of that weight from that air is evenly distributed, that's exactly what's happening. That air pressure is pushing on all sides of your body. So I got a little bit of water here to show you guys. So I've got my bottle of water, and it's filled about that much up. And on each side, I have some little push pins. So what I'm going to do is I'm going to take out one of my push pins. And I want you to let's make a hypothesis. Do you guys know what a hypothesis is? Basically, a hypothesis is just a big fancy word for a guess. So here's my hypothesis that I want you guys to guess. If I take out one of my push pins, what will happen to the water inside? Ooh, make those hypotheses, sigh. How many of you think that if I take the pin out, the water will come out? All this water that's inside, there's a lot of water in there. Okay. All right, well, how many people think maybe for some reason no water will come out? Okay, should we find out? There's only one way to find out. All right, ready? Here we go. And 3, 2, 1. He smokes. Look at that. There is absolutely no, I mean, there's a little bit of a drip, but the water isn't spouting out like that. Well, I have an idea. So we've got this other side here too, this other push pin. So do you think that if I take this pin out, all that water will come out? I mean, then we'll have 2 holes, so that's got to be something, right? Okay, hypothesis time. Who thinks water will come out? All right, how many think no water will come out? Okay, all right, time to try it out. 3, 2, 1, boop. I swear, these things were all the way in there. What happened? Well, here's the big question. Why is the water not spouting out the sides? Huh? You guys remember what I was talking about earlier? Do you remember that air pressure? Do you remember the weight of those gases pushing on all sides? That, my friends, is how strong air pressure is. Those holes are just the perfect size, so that weight from the air is pushing against it and keeping those holes closed so that water can't come out. Now, here's another time for another hypothesis. I've got the lid right here on top. What is going to happen if I take the lid off? Oh, mama, what's going to happen? So if I take the lid off, I put the lid away, what's going to happen? How many of you think nothing will happen? How many of you think that water is just going to trickle out just a little bit? How many of you think the whole thing is going to explode and get all over me? How many of you really, really want to see it get exploded and all over me and laugh at me? Yeah, I figured. Okay, so we're going to take the top off on 3. Everybody ready? Okay, 1, 2, 3, and let's get that top. Okay, perfect. Well, let's check this out. So if you guys see, and I hope so, because I know it's a little dark. There we go. You can see that now there is water coming out both sides. So some of you may be wondering, well, why is there water coming out on both sides? Remember how we were talking about that air pressure? So earlier, air pressure is coming from here, air pressure is coming from here, and it won't let that water out. But now, where's the pressure coming now? That air pressure is coming from the top. All that additional space right there is able to push the water down here, and the water and the air pressure from the top is stronger than the air pressure from the sides, and so it comes out like this. Now, what do you think will happen if I close this up and squeeze it with the pressure and with the force from my own body? You guessed it, boom, just like that. So it talks all about force, all about that pressure. So that's exactly why Sylvia Earle couldn't just go down to the very bottom of the ocean by herself. That's why she needed her own gym suit to make sure she stayed absolutely safe. All right. Time for another kind of science. Now, this is a really cool science. I just found out about this science a couple of days ago. So this science is called ethnobotany. Oh, that's a tricky one. All right, anybody know? Anybody know? It's okay. If you don't know, that's okay. But here's the thing, even I didn't know about this. Does anybody know what ethnobotany is? And it's not fair if you look it up on your phones. Anybody? Okay. Let's look, my friends, the Greeks. So we got to kind of spell this out. We got to take our time. So first of all, we've got to take the first part, ethno. Now, ethno is all about things like culture and all about things like ancestry and where you come from. That is ethno. Okay, so we got that, ethno. Then there's botany. All right, botany. Now, botany actually connects to plants. So here's how it works. Ethnobotanists study the culture and ancestry of people and sociology and how they relate to plants. I know that sounds kind of weird. Go away. I know that sounds kind of weird, but I'll show you what I mean. There was actually a woman named Isabel Abbott. And Isabel Abbott, she's still alive, and she lives in Hawaii. And Isabel Abbott is actually known by a lot of people as the seaweed lady. I know that's kind of a weird nickname for people to call you, but she's called the seaweed lady. And the reason she's called the seaweed lady is because of her Hawaiian upbringing and culture. She spent a lot of time learning about the way that in the early days, Hawaiians used to treat people if they ever had any sort of sickness or malady. And so you didn't always have a shot of penicillin or, Robitussin or something like that. And so what she goes back to is something that came from the earth, that botany, that plant work. And she actually connected it to seaweeds, those weeds that grow in the ocean. And if you ingest some of these seaweeds, they can be good for your immune system, help you keep diseases away. It can be good for your gut health to make sure that you're processing everything okay down there. Now, does that mean that you guys should go out there and run into the water right next and then just start scarfing down? No, that's not what you do. But still commonplace, a lot of people eat seaweed every single day, like kelp. Now, this is a fun part. I've never had kelp myself. Some people have had like sushi before. Maybe some of you have had these before, but this is dried kelp. Now, actually, maybe we can get an overhead shot of this so you guys can see just how pretty this is. So this is dried kelp. It's a dry kind of seaweed, and people eat this a lot. They eat it so it's good for their health, good, there are great things about it. It's very low sodium, but also it's gluten-free. It's not processed. There are no carbs. There's just a little bit of sodium. There's no fat. It's keto-free. It's vegan. Pretty much all those great things is in this thing. So I mean, it's also better for you than a potato chip. So I'm about to learn all about what a kelp chip tastes like, just in front of you guys. So you ready? Okay, 3, 2, 1. It's good. I swear. It's actually pretty good. Do you guys like sushi? There's kind of some sushi taste. This is kind of a weird question. Does anyone here like Brussels sprouts? See, I like Brussels sprouts, but I like them a little bit crunchy. It tastes like crunchy Brussels sprouts. One more. Definitely. I never would have thought that seaweed or dried kelp would be something that I'd want to eat, but you know what? If I had this with my lunch every day and it's good for me and it's good for the planet and natural, I think I'd totally eat this. So, thank you very much. I never would have thought of that. Ethnobotany. I never would have thought of that. Just to cleanse the palate a little bit. Now, this is a science that I think everyone here will know about. Does anyone here know about the science of paleontology? Ooh, I can just hear so many kids going, I do. Anyone tell me what paleontology is all about? What do paleontologists study? Anybody? Yeah, a lot of people are saying dinosaurs. You're absolutely right. They study dinosaurs. They also just study, all the leftovers of life on the planet from hundreds, thousands, millions of years ago. So it's not just dinosaurs, but I mean, if I was a paleontologist, I'd focus all about dinosaurs too. I think you're absolutely right. So there was a paleontologist named Mary Anning, and Mary Anning was the very first female paleontologist. It's a pretty big deal. So I think Mary Anning was about 300 years ago. Now this is gonna blow your mind. Mary Anning, her parents are paleontologists, her dad's a paleontologist, so she's kind of in the field and she's hanging out and she's like, oh, this is a cool thing. Oh, this smells weird, whatever. So she's rooting around by herself one day and she finds this weird little bone and she shows somebody and there's like, I don't know what that goes to. And she's holding it up to the other one, doesn't make any sense. And then she finds another piece. And then she finds another piece. and she puts together an entire dinosaur. I mean, not right there, but she's able to discover all of these bones. She is not only the first young woman to be a paleontologist, but she found her very own dinosaur. And here's the even mind-blowing part. She's 12 years old. See, remember what I told you about the great minds? She's 12 flipping years old, and she was able to find an entire dinosaur. I mean, do you guys think that you'd be able to find an entire dinosaur? Sure, why not? Just go grab a shovel, start digging. I don't know. I mean, that's what happened to her, sort of. Well, I don't have a dinosaur with me. I'm very, 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 very sorry. But if my friend could give me an overhead shot, I do have something that came from a real dinosaur. It's this thing right here. Now, some people may have seen something like it before. Other people may not have. But let's take a look at it. Now, this is, I'll give you some hints about this. This came from millions of years ago. It was actually found in North Dakota. And so I'm going to show you some cool things about it. This probably weighs about 2 pounds or so. And it kind of has an ovalish shape, but then it's pointy at some ends. It's kind of got a weird, almost kind of looks like an old potato. But then I look at sides like this and it gets really, really kind of some cool colors in there. Some little, I don't know what this red part is. Then you've got this textured area right over here. So it's kind of this look to it. So let's see, if you guys found this in the ground and I told you this came from an actual dinosaur, what do you think it is? Look at the shape. Look at the colors. No, it doesn't really have a smell. I would promise. Maybe it's not really sharp, but it used to kind of have a sharper edge. So maybe millions of years ago, this used to be really sharp. Now, let's see. I'll tell you another hint about this dinosaur. This actually came from a brachiosaurus. Now, some of you may be looking at this and you're saying, well, it looks like it's kind of pointy. This must be a tooth. Well, a brachiosaurus only eats plants. And brachiosauruses are not meat eaters. So they are not carnivores. And only carnivores had sharp teeth. So we know that this did not come from that. All right? This is not a tooth. Maybe a claw? No. Maybe a toenail? No. Any more guesses? Should I tell you? You ready for this? This is dinosaur poop. This is actual dinosaur poop. It's safe for me to touch, but it is fossilized dinosaur poop, and it is everywhere, and paleontologists are finding this stuff all over the place. In fact, when dinosaur poop is pressurized in over thousands of years, it hardens to like this. It has a special name. It's called coprolite, and this did come from a dinosaur. It's very, very hard. It's safe for me to touch because it's been pulverized. There's no bacteria in it or anything like that. I just keep it on my desk because it's a cool little paperweight. Some people, they put them in like rock polishers and make them into jewelry or things like that. And I read somewhere that if you find coprolite that's in the perfect shape, you can get like tens of thousands of dollars for it. I don't know how much this was, but I love telling people this is dinosaur poop. And I love giving it to people and saying, check this out, because they'll look at it, they'll put their hands all over it, but no, it's dinosaur poop. So chances are when you're just walking around outside, you're probably stepping on a lot of dinosaur poop that's underground, and who knows what's maybe in your sandbox at home. I'm just saying. All right. So I want to show you, let's see, a couple more things. Oh, you know what? Before we go any further, let's check in on my lead strip. So I still have it right over here. Now, it's just like one of those strips for the COVID test. I don't know if you guys have had the COVID test, but we have to make sure of something. We have to look at the strip and we've got to make sure of something. We've got to make sure that the blue line, there's going to be two lines. Got to make sure that the blue line that's very, very dark is on the left-hand side, this side. If the blue line that is very, very dark is on this side, that's bad news. I don't know what's going to happen. How many of you guys think that it's going to be super dark on the left and that we're okay? Okay. How many of you guys think that it's going to be super dark on the other side and that we got to do something important? I don't know. Let's find out. Oh man, what a relief. The super dark side, well, it's not, I'll show it the other way. It is on the left-hand side, and that means that our water here at the Omaha Children's Museum is safe and does not have any excess of lead, which is good news. Boy, that was kind of scary. I wasn't sure what was going to happen. Now, there's all of these different kinds of sciences, every single one. So I've got another one for you, all right? Last one. Well, maybe. Last one, physics. Physics. Doesn't have any of those otnies or ologies or anything like that. Physics. Anybody know about physics? It's a big one. All right. Okay, so physics is, remember this? Okay. Physics talks all about how everything is comprised and the nature of everything. Now, I know you're like, what does that mean? Well, when I say the nature of everything, I'm not talking about like trees and birds and everything. I'm talking about the nature as like how it is and why it is, and how does the force of everything and the reactions, the nature of the world, also maybe the universe. In fact, we're going to be talking about astrophysics. So astro, the giant space, planets, universe, galaxy around us. Astrophysics, that's a lot to take on. So my favorite guy that I just learned about, named Michio Kaku. So he's kind of looking into the field of time travel. Is anybody here into time travel? I am totally obsessed with time travel. Anyone like time travel movies? Do you guys have a favorite time travel movie? Bet some of the grown-ups really like Back to the Future, or maybe Bill and Ted's Excellent Adventure, maybe? Okay, big question. How many of you guys like Avengers? Yeah, I figured. But they talk about time, right? You have to go back in time and stuff like that. So it's something that everyone is interested in. I'm super interested in it. And Michio Kaku, he's an actual astrophysicist. He studies these things and he's trying to figure it out. So tell me something. Do you think that we can travel forward or backward in time? Do you think we could ever do it? You don't know. Well, there's been a lot of super smart people that have been trying to figure it out for a long time. So Sir Isaac Newton, remember the apple fell on his head and he figured out what gravity was? Sir Isaac Newton, he says that no way, can't happen. He said that time is like a river. Sounds like a song. Time is like a river. It is always going at the same speed. It will never stop. It always goes in a straight line through everything. All right, cool, that's your theory. Let's see if you can prove it. He couldn't. Moving on. Then there's Einstein. Remember? Fuzzy hair, fuzzy mustache. So he says, not so much, because when you think about a river, rivers get really fast in some parts, so then they get slow, then they get bigger or smaller, or they split in this way, or they get into a whirlpool. And he talks about the theory of relativity. All right, so good. So moves on, he can't really prove it. Moving on. Then we go to Stephen Hawking. Stephen Hawking, he goes into a long talk about it. He's like, I don't think it's possible at all. If we wanted to travel forward in time, we'd have to travel at the speed of light, which is 128,000 miles a second, super duper fast. No one can go at that speed. And if we wanted to go at that speed, we'd have to go with an infinite amount of mass and an infinite amount of energy, and it would be absolutely catastrophic and possibly blow up the entire galaxy and all the other galaxies around it. Okay, well, we still can't prove it. So now we've got Michio Kaku, and Michio Kaku says, okay, there's that, but what if we've got these alternate dimensions and different universes? Maybe that's something going on. The thing is, we still don't know. These are four different great minds all talking about the same thing, but they still don't know for sure. And some of them go back hundreds of years, and some of them go back to yesterday. Now, I don't have any way to show you guys if time travel is doable or legit. A lot of astrophysicists are saying it can be done. They're just not quite sure how. But I'll show you a way that we can kind of do it. If I could get my overhead switch, please. So let's talk about our solar system. So our solar system, you know, we're in it, and there's the sun, and there's all the planets that are going around us, and we're in the galaxy, the Milky Way. So that's our galaxy. So let's pretend that I have this cow right here. This cow is going to be the Milky Way galaxy, because I just made that up. That is hilarious. That is fantastic. So that is the Milky Way galaxy. I'm so filled with joy right now. So we've got the Milky Way galaxy over here. And then I'm thinking of the closest galaxy to the Milky Way galaxy is about 25,000 light years away. And it's called the dwarf Canis Minor. So think of the size of the cow. That's the Milky Way galaxy. Well, the dwarf Canis Minor galaxy is a lot smaller. In fact, compared to a cow, it's about the size of a mouse. Okay, so I know these aren't exactly the same, but remember, so this is the Milky Way, and this is the dwarf Canis Minor. So these are two different galaxies, roughly about 25,000 light years apart. So obviously, we can't travel from here to there, because in order to get to there, we'd have to travel at the speed of light, which we can't so much do yet. But let's say I have a hugely powerful telescope. This isn't a real hugely powerful telescope, but I'm going to use it to show you guys as an example. So let's say I'm on this side, I'm in the Milky Way galaxy, and I'm going to take my super duper telescope, and I'm going to point it at my friend. Let's do it like that. That was a very uncomfortable end. So he's going to point it this way toward his friend in the dwarf Canis Minor. So it's much, much smaller. So this is 25,000 light years away. Now, since it's so far away at such a long distance, at such a distant period of time, when the cow looks all the way to the mouse, he won't be seeing what the mouse is doing at the exact same time that the cow is looking at it. The cow will be looking at the mouse and seeing what the mouse was doing 25,000 years ago, because it takes all of that light, 25,000 light years, to get to this surface. So the cow is looking back in time to see this other galaxy. So in a way, the cow is a time traveler looking to the past. Now, if he were to find some way to look forward to us, he would see us maybe somewhere in the future. Here's a really weird way to put it. If you were to say clap, I'm sorry, could you turn on the front lights? Thank you. Dig this. Let's clap together on 3. Ready? 1, 2, 3. That just happened in the past. That just happened in the past. It's just happened. That just happened. What I just said happened, that just happened in the past. That blows your mind. In fact, the sun is so far away from us that if the sun were to burn out right now, 8.5 minutes later, that's when we would know about it. So the sun could have burned out right now. Don't worry, it didn't. But the sun could burn out right now, and its light takes such a long time to reach the planet Earth that we wouldn't know it for another 8.5 minutes. So all of that heat, all of that light would just disappear, but we wouldn't know it for such a long amount of time. I think that's the coolest thing in the world. So, more great minds. Even though some great minds are finally discovering new things, they're always working at the same time. That's all that terrific stuff. I want to show you something about one more great mind that I'm really excited about. Now, this is a live demonstration that I'm going to show to you guys, and this is something that you'll be able to create at home. I'm going to send out the information, the instructions, the materials on everything you'll need, but I thought I'd show you how it works right now. So this goes back to a guy named Omar Khayyam. This is about 1,000 years ago. Omar Khayyam, he's an astrophysicist as well, and he learns all about how the planets work and how the Earth revolves around the sun, and how even though the Earth is revolving around the sun, it's also turning. He's keeping in track of that. So what he does is he's developing his own solar calendar. Now we have our clocks and we have our calendars on the walls and all that stuff so we can keep track of those things. But 1,000 years ago, we didn't. So we were able to look, well, Omar, was able to look at the pattern of the sun's light at different points and figure out roughly what time of the year it was, what date, all just by looking at patterns of the sun. Now, I'm not able to make a solar calendar for you guys, but I'm going to have something a little similar that you can make at home. So for a few of these things, can we get an overhead shot of this, please? You're going to need a few of these things at home. All of them are really super easy to get. First thing you're going to need, just a square of cardboard. This one is about 10 or 11 inches, but it doesn't have to be perfect. The next thing you're going to need is a paper plate. I think this one is about 9 inches, but again, it doesn't have to be perfect. You're going to need a ruler to make those measurements. You're going to need some tape. And you're going to need a pencil. Doesn't have to be sharpened. And you're also going to need some sticky tack or some mounter's tack. It's that little stuff you put it into a ball. You can help put stuff on the wall without it tearing or anything like that. So you're going to need just a little bit of that. If you don't have that, you could also use clay or putty, things like that. So the first thing we're going to do is I've got my center marked right here on my piece of cardboard. And I just did that using my simple ruler right here, 11, marked off 5.5, 11, 5.5, because I am a brilliant person. And I'm just going to take my rolled up ball, remember, just the way we were talking about how pressure works on all sides. If I push on all sides of that, it makes that sphere. Brilliant. I'm going to push it down right there, right smack dab in the middle. Now I'm going to take my pencil and I'm going to push it down, eraser side first, right down all the way into that putty. And I'm going to smoosh that putty on there, make sure it's sticking up straight, just like that. Perfect. So when you have a chance, make sure you take your paper plate and find the center of it. Again, it doesn't have to be absolutely perfect. I just took my ruler and I was able to find the center point. And you're going to make a small hole with it. I was wrong. You're also going to need some scissors. You may need some help from an adult to get this part. But I'm just going to make a very small hole right here in the center. So what you're going to do is you've got this sticking straight up. It's doing a great job. And you are going to essentially just poke your pencil through the hole in your paper plate. Don't pull the pencil up. Make sure it stays sitting on the actual clay right there on the piece of cardboard. It doesn't have to be totally secure, but you want to make sure that you're not lifting it up. And once you do that, you just might have to ease it. Oh, perfect. Beautimous. Awesome. Perfect. It's going to stand up straight like that. Now, I like to be super, super, super safe. So what I did was I am just making sure everything is taped in place. So I'm just going to tape my edges here. First of all, I'm going to make sure that the paper plate doesn't come off of the cardboard. And I'm also taping it right here, right where that pencil meets the paper plate. That way, in case things get a little slippery between the hole of the paper plate and the hole of the, and the pencil, it won't get too damaged. So it should stay upright just by giving it a little bit of extra help. So what we're creating here, in case some of you don't quite know, is we are creating a sundial. And a sundial is kind of like a ruler. This ruler is meant to measure length. A sundial is meant to measure time. So right now we have clocks, we have watches, we use those to measure time. But a sundial is something that we've been using for thousands of years. And I'll tell you exactly how it works. Now it's so beautiful, you see, it's all set, that's all we have to do. I don't know if you want to get super duper, tapey and get a lot more tape on there, but truth is, I think this is in a pretty safe spot. I don't know, maybe you want to color it, go bananas. So what we are going to do is you're going to take your fantastic sundial outside. Take it and put it in a nice, flat, dry, even space. And let's say you're going to start off at about 10 o'clock in the morning, nothing too long. And at 10 o'clock in the morning, I want you to look at the shadow that your sundial is casting. Now it's a little tricky in here because right now I'm indoors and I have light sources from multiple places, so that's why it's making 3 different shadows. But tell me something, if I go outside, where is all the light coming from? You guys know? It's coming from the sun. So we're only going to have one source of light, and that shadow is only going to go from one space. So let's say you go outside, you put your sundial flat, and your sun is casting a shadow. Let's say this one right here. All you got to do is take a marker and just mark that right there. Now we said that that was going to be about 10 o'clock in the morning. So maybe you want to make the number 10. So then set your alarm for an hour later. And let's say an hour later, your shadow has moved a little bit. Now, when you're doing this, don't move the sundial. All you have to do is keep checking in. So it's now an hour later, so another hour is going to be right there. I'm just following that shadow, and we're going to make it 11. So keep doing this for the rest of the day. Pretty much keep doing it as long as the sun is out. Do it every hour to see how that shadow moves throughout the day until the end of the day is going. And then, from then on, anytime you look at that sundial without having to look at a watch or a clock or anything, you'll be able to look at the sundial and say, oh, it's 10:30, because you have the shadow right here between 10 and 11. So just so you know, if you take your sundial and you move it to a different space, outside, or it's on a hill, or it's all the way sprung out, it's not going to look the exact same because the sun won't be hitting it from the same angle. So if you do move it, make sure you're hitting it at the same angle. So make sure you go out there at 10 o'clock and make sure that that sun will come down at that same area so that it lines up. Then you have your own sundial, your own homemade version to tell what time of day it is, your own clock. Pretty cool, huh? So we'll make sure that we get those instructions and that materials list out to you guys. I'm sorry we couldn't have it for you earlier, but like I saw, I mean, that was a pretty quick way, pretty speedy way to get through all that stuff. It doesn't take very long at all, and it's really, really easy. So yeah, I thought I'd show you guys a little bit about the great minds. There are more great minds than this. I mean, this is just, I didn't have a lot of time to tell you guys all about them, but I tried to show a demo of, everything. And I love the fact that some great minds are still trying to figure something out, and they're kind of agreeing and they're disagreeing. And I also love that there are great minds that are really, really young, and it's not necessarily a super old dude that has to go all to these schools and be really rich, but just kind of anybody, someone just like you. So it's all these different great minds that are everywhere, developing new things, ideas, inventions, theories, and you should never overlook them. Guys, thank you so much for watching. I'm so glad you checked it out. I hope you had a fantastic time.
Wonderful. Thank you so much, Ben. We packed so much science into so little time. And if you have time to stick around for just a couple of questions, we had some pretty great minds in the audience today who had some thoughts and some things that they wanted to know. Now, we talked a lot about some pretty impressive scientists who all started out with a big idea or a big discovery. But can some scientists have an interest in science without having to get started with a big idea? What are some other ways we can get involved in science, even if we haven't made a great big discovery to do it?
I think that's a great question. Sometimes people may be a little bit afraid of science because it takes them a little while to really understand. I mean, I was talking about time travel a second ago, but I'll tell you what, time travel is exciting because, people saw it in the Avengers movies and they thought it was cool and they didn't really know how it works. And so maybe you can be struck by something or see something that you find very, very interesting and just want to learn more about it. Has that ever happened to you guys where you see a dinosaur movie and you want to learn more about dinosaurs? Or maybe you really get excited about snakes, or you have a pet snake, so you want to learn more about your pet snake, or things like that. Maybe you are really excited about apps on your phone and you're like, well, how do those get made? Or how do I do that? Or could I make something like that? I'm what you call a passive learner. I have a tough time going out and finding new things, but if I see something that I really get interested in, that's what I get excited about. And I want to actively go out and learn about those new things. So don't feel like you have to be super smart or have to push yourself into those different sciences. Do something that you love. I think all of these scientists that came up with all these fantastic theories and ideas and discoveries were all passionate about what they did, and they wanted to invest their time and also share it with the world.
Awesome. That is wonderful. Now, we also talked way back toward the beginning of our lesson about some pretty impressive scientists in some pretty specific fields. And we got to see the great big astronaut-like suit that we use to go underwater as an oceanographer. And we had some questions around whether that might be a physically demanding thing to do. So do you have to train to be an oceanographer, an astronaut, and are there any other unusual things that specific fields of science require you to be pretty good at?
Well, that's a wonderful question. I mean, obviously, some of these people had to maybe go to school for a lot of time. Sometimes they have to get things like degrees or get employed with certain people, also be able to work with some of these other, sometimes it takes a lot of work. I guarantee this idea just didn't come up in one day. I think there was a huge group of people that were working together. So, I mean, this suit obviously took some time, took some work to put together. Sometimes it just takes one person to kind of think outside the box or have one question that maybe not everybody else did. So, I mean, for example, I've got dinosaur poop here. I don't think anyone in all of those paleontologists were digging, actively looking for dinosaur poop. I think this guy was like, I'm looking for a T-Rex and I'm looking for a Dilophosaurus. There was probably not one guy going, I only want to find the poop. But there was one person that kind of had an interest in it. And so I think there's a special direction, a special little niche for everybody. Or if not, someone else that they can share that interest with.
That is amazing. Now, it is getting to be about that time, but as perhaps one final question, and perhaps the most frequently asked, we talked about a lot of really incredible scientists from throughout history. So everything from way back in the 1800s with Mary Anning to more recently with the lead poisoning experiment by Gitanjali. So one theme that we saw was, to your point, that we didn't necessarily have to be old with poofy hair and a beard and mustache to be a successful scientist. So do you have any final advice for some of the younger students in our audience on things they can be doing now to explore the field of science?
That's a great question. I say that a huge part of it for me was, I'm going to give the example of time travel again. I knew that I wanted to talk to you guys about time travel, but I don't have a time travel machine here to show you anything. I can't prove, I'm not I don't have the time or anything like that to study those things. But I got interested. I seriously did a lot of outside research. Some of the people I work with are rolling their eyes right now because I bugged them so much because I was reading books and looking online and saying, hey, did you know this thing? I just couldn't stop. I got so obsessed just learning one little thing. So essentially what I'm saying is, one little thing gets you excited. Keep learning about it and never lose interest in learning. Never forget that you're never done learning. If one thing excites you, learn more about it, pursue it, find out everything you can, and maybe find out some other things like poop. It's a very important thing, and it relates to everyone.
Wonderful. Well, thank you so much. As we've said in some past classes together, that curiosity is really all it takes, that desire to learn more. And thank you for everyone by kickstarting that desire by being here in today's class. We hope to see all of you again in another Varsity Tutors Star Course sometime very soon. In the meantime, thanks so much once again to Ben and the Omaha Children's Museum.
Thanks
Bye,
so
everyone.
much, guys. Have a great day.